here's a quick lesson for you, hopefully reminding you if you forgot, on how to solve linear equations. You've been doing this in algebra and you've done it in geometry, but it never hurts to make sure we're all on the right page. First, again, we have to start with the vocabulary, and now instead of talking about expressions, we're talking about equations. So an equation this time, you will see an equal sign. And also, it tells you that you have a complete sentence. An expression, remember, is a phrase or a part of a sentence. An equation is a complete sentence. So it is a statement, or it's defined as a statement that has two expressions that are equal. A statement that has two expressions that are equal. Okay? And we've learned to solve those in the past. A linear equation gets a little more specific. It has one variable that is to the first power, and it's an equation that can be written in the form ax plus b equals 0, and that might sound familiar. So it's an equation with one variable. Remember, when you graph it, you get a line. It's to the first power. And you can write it as y equals, let's say, mx plus b. Does that ring a bell? But they left it a little more generic in the book, and they said ax plus b equals 0. And in this case, a and b are just numbers. So x really is your variable in this equation, but it's more important to realize it's to the first power. Anytime you have an equation that only has a variable to the first power, it's going to give you a line. A solution to an equation is a number or an answer. That's what you're always looking for, the answer. But it's a number that that you get when you substitute it back into the equation. So let's just say a solution is an answer. That's the most straightforward. Okay? And equivalent equations, and this becomes important again later, are two equations that have the same solution. Two equations that have the same solution. For example, x equals 2, and it works in two different equations. Looking at this table, these are all the justifications for why we are allowed to solve equations the way we do. We have the addition property of equality. What that says to us is if we have a and b and we add some number, let's say 2, to both sides, we still have equivalent equations. We're allowed to do that. As long as we add the same number to each side, you are not changing the original equation. The subtraction property of equality says kind of the same thing. If I take the same number away from both sides, I still have equivalent equations, so I am allowed to take the same number away from both sides, as long as I do it from both sides. Multiplication property, you can probably guess, I'm allowed to multiply both sides of that equation as long as it's by the same number. I am not fundamentally changing the problem. And the division property of equality says I am allowed to divide, and I'm just going to use the side symbol. I'm allowed to divide one side by a number as long as I also do it to the other side. And then I get into how I like us all to remember these, and I use these words a lot. When you're solving equations, you have to remember your goal. Your goal is to get the variable alone. Sometimes if you keep that in mind, it helps you solve these. So I'm going to write get the variable alone. Okay, well, how do we do that? We do that using inverse operations. Inverse operations are operations that undo each other. Sorry, this is messy. Operations that undo each other. What do I mean by that? All right, this is what I mean. If I have addition and I need it gone, how do I undo addition? Well, I subtract. Okay? If you have subtraction, how do you undo that? You add. Again, if you have multiplication, how do I get rid of multiplication? I divide. And if you have division in a problem and you want the number to go away, how do you undo that number or that operation? You're going to multiply. And you'll see me using this example below in example 1. And then what I like to call the golden rule of algebra says, whatever you do to one side of the equation, you better be doing to the other side, or you are fundamentally changing the problem, and that is not what we're trying to do. So the golden rule of algebra says, whatever you do to one side of the equation, whatever you do to one side, and I mean like left or right of the equal sign, you must do to the other. Sorry. Hopefully your paper's big enough and you can write notes. So let's go ahead and we're going to solve this equation. It jumps right to a two-step equation. So you can see in here, I have a couple operations going on depending on how you look at it. I have an addition and I have a multiplication of this fraction times that x. You could also look at this as not a fraction, but you could look at it as 4 times x and x divided by 5. I'm going to look at this one as 4/5 x, the fraction, because I'm going to show you a shortcut way to get rid of that in one step. But the key to remember is when you have a two-step equation, one involving multiplication and division or addition and subtraction, you must always get rid of the term that is being added or subtracted to the x. I like to call it the dangling term. It's like this is my prize and my thing I want to get a loan, and this is kind of hanging off it. So we are going to get rid of that first. It's being added to x, so if I want to undo that addition, I'm going to subtract 8 from both sides to undo it. Why did I do that? Because 8 minus 8 is 0, so these are gone. I am left with 12 on the right side of my equation and 4/5 x on the left side. Sorry, that's messy. Now notice I'm writing all these steps down, and I expect you to write all these steps down for our first chapter. Once I see that you have a good grasp on this, we can start skipping steps. So 4/5 x equals 12, and I want 4/5 to go away. So what I'm going to do is I'm going to multiply by the reciprocal of 4/5, which is 5/4. The golden rule says if I do it to one side, I better do it to the other. So I'm going to go ahead and do that right away. The reason I did that is because in one swoop I've just gotten rid of both of these. If you multiply this fraction, you have 20 over 20. Well, that's just 1. So this has canceled each other. These must be multiplicative inverses, if that rings a bell, because when I multiply them, I get 1. So I finally have x isolated on the left side of the equation. I now just need to finish up and clean up the right side by simplifying. So I'm going to choose to do 12 divided by 4 first, because that's 3, and 3 times 5 is 15, which is easier. But go ahead and do the 12 times 5 and get 60, and you could do it that way as well. But you've isolated your variable, therefore you have solved your equation. You know what that unknown letter represents, and it turns out to be 15. Go ahead and do these at the bottom, and come back, and we will check it together. All right, here are your answers for 1, 2, and 3. I tried to do things in different colors so we could keep it straight what I was doing. Nothing very surprising about number 1. Number 2 I think is okay. Let me know if you have questions. Number 3 again is the interesting one where we had the fraction and I multiplied by the reciprocal. But notice that when I multiplied, I took the negative sign with me. You want to include the negative when you're multiplying, because if I didn't, I'd be left with a negative x in the end, and I'd have to do a whole other step to get rid of that. So go ahead, if you see a negative, multiply or divide by the negative right away, because those two negatives make a positive, which leaves you with a positive variable at the end. If there was a negative variable, you're not done because you have not isolated that variable. Example 2 is one where sometimes you need to write a linear equation before you can solve it. So we'll read it together. It says, during one shift, a waiter earns wages of $30 and gets an additional 15% in tips on a customer's food bill. The waiter earns $105. What is the total of the customer's food bills? So we need to start off and write down. Well, not everybody likes to do this, but it sometimes helps. How much is this guy making? Well, that's called his income. So we are going to know that his income is made up of his wage, which is the $30, and then you have to add to that the percent he gets on tips, oops, that says percent, times the actual food bills of his customers. You don't always have to write this out in English, but sometimes it helps. And then we fill in what we know. Well, we know his income for the whole thing was $105. His wage was the $30. They told us that up there. And then he gets 15% of his food bills. Now be careful, you never use the percent in an equation. You always turn it into its decimal version. Percent means per 100, so 15% would turn into that decimal. And then his food bills, well, we don't know how much the customer's food bills are, so that's X. So let's go ahead and solve this problem. The first step I would do is I would subtract 30 from both sides. Oops. Okay, and then I end up with 65 over here, right? 100 minus 30 is 70, minus 5 more 65. And point or decimal or 15/100ths on that side. So take your calculator now, because we're going to have to clean up this problem. And let me change the color. And now I would divide by that 15/100ths. All right, so grab your calculator, take 65, and then you get your answer of $433.33. All right, example 3. What if you have variables on both sides of the equation? What do you do? Well, don't panic, number 1. You need to remember that when you have a variable on both sides of the equation, you just need to use inverse operations to get them on the same side. Remember, your goal is to get p alone. And so we want p on either the left or right side of the equation. The choice is up to you. And we want all the constants on the other side. So I could either take away 9p from both sides, or I could take away 7p from both sides. It doesn't matter. It's your preference. A lot of us like positive variables, and so that would mean that we should move this over here. But also a lot of us like all our variables on the left-hand side. So again, it's personal preference. So I am, just for fun, going to take away 9p from my right side and put it over on the left, or do the same thing to both sides. On my left side, I'm left with negative 2p plus 13. And on my right side, I am left with a negative 5. Make sure you watch your signs. Sorry, that's so messy. That says negative 2p. Negative 2p. So keep working to get your p isolated. Now I have my variables together, so you should feel better. This is a two-step equation. Remember, we always undo the dangling term, or the term that's being added or subtracted. So I'm going to subtract 13 from both sides. So I'm left with negative 2p on the left side and negative 18 on the right. And remember, I said if you have a negative sign or a negative coefficient, you want to divide by that negative as well. So I'm going to divide by a negative 2, and then when you clean it up and simplify, you end up with a positive 9 for p. Go ahead and do the guided practice problems at the bottom, and then we will get back together. And there are your answers for problems 5 and 6. Sorry, they're a bit messy. I'm working with a stylus, but go ahead and stare at those. And if you got them wrong, go ahead and try to do them again. Like, turn off the video or whatever and go do them again, and try to fix your problems. Or maybe the teacher made one problem and you want to go correct her. That's fine too. All right, example 4 is one in which we need to use the distributive property, and they just throw everything at you this time. So if you can do this problem, you can do any problem. This problem has distributive property on the left side, distributive property on the right side. I'm seeing this might have to be combined down the line, so let's go ahead and get started on this problem. First, we're going to distribute. So I'm going to do 3 times 5x, which is 15x. And 8 times 3 is 24, but it's going to be negative because of that minus sign. On the right side, you're going to end up with a positive 2x. And a negative 2 plus 7 is a negative 14. And then I have that negative 12x dangling out there, which I have to write down. Your next step, and this should be the one, you have x's all over the place, but I have some that are on the same side of the equal sign. This is called combining like terms. So we're going to combine these like terms first, and I am going to get a negative 10x minus 14 on the right side, and I'm going to rewrite down the left side. You always write full and complete sentences. This whole line is equivalent to this whole line, so we have to write everything down. And now I have a situation where I have an x on the left and an x on the right. When we are using inverse operations to collect our x's, we call it just that, collecting our like terms. So I'm going to take that negative 10x and I'm going to add a 10x to both sides. And then I will end up with 25x minus 24 on the left and a negative 14 on the right. Well, let's keep going, but now it looks a lot simpler. I have a two-step equation. Our first step is always to undo the added or subtracted term first. So we need to add 24 to both sides. And I will move over and write over here. So I have 25x on my left side, and a negative 14 plus 24 will turn out to be 10. Now don't panic, because it looks like we might get a fraction for an answer. Oh my, we will be okay. So here I have to divide by 25, and I'm left with x equals 10/25. That's a fine answer. Don't go running and grabbing your calculator and try to make that a decimal. Leave it like that. But if you want to be the awesome math student that you are, you need to simplify that fraction, which means divide out any common factors. Well, 10 and 25 both have a factor of 5, so I'm going to divide them both by 5. So 10 divided by 5 is 2, and 25 divided by 5 is 2/5. So in this problem, x equals 2/5. You go ahead and do the guided practice problems. See if you can handle 9 and 10, and I'll show you an easy way to do them. So here are your answers for 7 through 10. Go ahead and check them each step. If you need to redo them, go ahead and do that. I told you I would show you an easier way to do 9 and 10. If you chose to do it using common denominators and use fractions, you're totally legitimate in doing that. But clearing the fractions is another method to use that is quite simple and straightforward, and you would really come to appreciate if you attempted learning it. You can notice that I had all these fractions and all of a sudden they're gone. Well, what did I do to get rid of them? I look at the denominators of my fractions and I need to find a common multiple of both of them. The lowest common multiple would be the best. Between 4 and 5, the lowest common multiple is 20. So I take that 20 and I multiply it by both sides of the equal sign, the left and the right. And then what I do is I distribute that 20 to each number. It sounds scary, but it's not, because when I look at this first term here, 1/4 x, and I multiply it by 20, you're really just taking 20 divided by 4, and that's your 5. 5x is your answer to that. 20 times 2/5 x, your 20 divided by 5 is 4, times your 2 gets you 8x. And then don't forget to do it to your other side too. Remember the golden rule, both sides. 39 times 20 gives you 780. And then you go through and you solve it very simply because you have no fractions anymore. So if this made sense to you and you want to try it for 10, stop the video and redo 10. The common multiple here was 3, between 3 and 6 and 2 happened to be 6. And remember, you distribute it and then you end up clearing your fractions, meaning there are no fractions left in that equation, and it turns out to be very straightforward to solve. Practice with that technique. You'll be very happy you did. Thanks for listening to my lesson. Good luck on your homework, and again, let me know if you have any questions.